Dear Chem 253 lab students, welcome to Lab 4, the oxidation of cyclohexanol to cyclohexanone. I'm Professor Lashley, and I'm going to walk you through some of the things you need to know about this lab. You're going to perform an oxidation of a secondary alcohol called cyclohexanol into a ketone called cyclohexanone. The oxidizing reagent you're going to use is called sodium hypochlorite or bleach, and you're also going to use acetic acid or glacial acetic acid rather as a catalyst in this reaction. Glacial acetic acid, by the way, just means that it's super pure acetic acid. Now, this oxidizing reagent combo, bleach and acetic acid, is not something you would have probably was not covered in your organic chemistry lecture. And definitely you have most likely, I'm going to say, not seen the reaction mechanism, which I'm about to show you in the next slide. Now, this is not a mechanism you need to worry about memorizing or anything, okay? But I do want to point out a couple of important things about this mechanism. So at the very beginning of this mechanism, to the left, we have the sodium hypochlorite react with the glacial acetic acid in a protonation step. Once the hypochlorite's been protonated, it's going to react with the cyclohexanol, which is a secondary alcohol. And a couple of things I want to highlight in this reaction is that we're going to lose two very important protons. The first proton is over here. That's a proton connected to the oxygen of the secondary alcohol. The second proton we're going to lose in the course of this reaction mechanism is this one down here. This one is connected to the adjacent carbon of the alcohol. Once we lose these two protons that I've circled in blue, we're going to form a double bond as a result of that. And this double bond is between carbon and oxygen. And so now we have fully oxidized a secondary alcohol to a ketone. The cool thing about this oxidizing reagent is that it's considered a green oxidizing reagent. What does that mean? A green oxidizing reagent is one that produces little to no toxic waste. In this case, the only byproducts of this reaction, so other than the product that we want, the byproducts that we're forming, they're water pretty much and sodium chloride. So these are super non-toxic species. Sodium chloride is just table salt, as you know. And so this is pretty much as environmentally friendly as it can get. As you may recall from lecture, some of the other oxidizing reagents, for example, the Jones oxidizing reagent, which is chromium trioxide, is super toxic. In fact, it's carcinogenic. So at this stage in your organic chemistry career, we don't want to have you work with some super toxic and dangerous things. So this is a very safe way for you to experience an oxidation reaction. Now let's go a little bit over the procedure and let me highlight some of the important things here. First of all, the reaction you're performing today is slightly exothermic. So for this, as a precaution, the second you get into the lab, the first thing I want you to do is set up an ice water bath, just in case that when you do the reaction, it goes a little crazy exothermically, you'll have that ice water bath ready to cool it down. Okay, so that's just a precaution. Have that ready right at the beginning of lab. Then you're going to start adding the reagents to one another. So what are your reagents today? Let me go back a slide and look at the reaction again. So we have the cyclohexanol, okay, the cyclohexanol over here. And then we have the acetic acid and we have the bleach. So what you're going to do is you're going to add the cyclohexanol and the acetic acid to one another. And then you're going to add the bleach to that dropwise. And you're going to use a SEP funnel for this. So the important thing is here that when you add the bleach from the SEP funnel to the other two reagents, that it must be done over a period of 20 to 25 minutes. It must. Okay. If you do this quicker, your reaction is not going to pan out well. It's probably not going to work out. Okay. So this is very important that you open the stopcock of the SEP funnel just very slightly so it adds drop-wise, 20 to 25 minutes. Definitely don't cut that short. Okay. Now, once that time has expired and all the bleach has been added, we want to make sure that there's no bleach left unreacted. And for this, we're going to use something called potassium iodide starch test paper. And this test paper just basically tests for any presence of bleach. Should there be any unreacted bleach left at this point, which is kind of likely to be honest, then the paper will turn dark blue. So this is probably going to happen for the vast majority of you guys, that the paper will turn blue. So that means there's still bleach present. So what do we do with the bleach? We kind of want to get rid of it at this point. The bleach is an oxidizing agent. So the way to get rid of it is by adding a reducing agent. And the reducing agent we're going to add is called sodium hydrogen sulfide. So we're going to add that until all the bleach has been reacted off and the starch iodide test is negative. Okay. All right. At that step, what we're going to do is we're going to add an indicator called thymol blue indicator. And then we're going to add 15 to 20 mils of a 6 molar solution of sodium hydroxide until the indicator turns blue. For some of you, this might require a little bit more than 15 to 20 mils, okay? So if the indicator just simply doesn't turn blue, go ahead and ask a TA or a professor for help, okay? But just as a heads up, it's going to be a very, very light blue, okay? So it's not going to be super dark. So, but anyways, if you have doubts, go ask for help. All right, so once you have this very, very light blue, we're going to set up a simple distillation apparatus, which is shown in figure 1 in your lab procedure. So the simple distillation is one you've performed previously in Orgo 1, but it is possible that you took Orgo 1 virtually, so you might only be familiar with the theory, but not with the praxis. So we're gonna help you with this, of course. When you set up this distillation, please do me a favor, do not, under any circumstances, start the distillation until a professor or a TA have given you the go-ahead. So we want to check your apparatus and we want to make sure it looks correct before you get started. A couple of things to point out here is that you're going to use a Bunsen burner, and you definitely want to add some boiling stones into here. So you're gonna have some boiling stones in here, and I'm marking in there. And you're gonna have 2 Bunsen burners in your jar. You want to use the larger of the 2 Bunsen burners for this. And the thermometer placement is kind of important. The thermometer should be just below the elbow of this adapter here. So this is where the thermometer needs to be. It should not reach into your flask or anything. The tubing that has water flow through the condenser over here should be far away from the Bunsen burner flame. Obviously, you don't want the tubes to catch fire, and water will go everywhere and it will be quite a mess, okay? You're going to collect your distillate in a cylinder over here to the right side of this schematic. One thing that's important and a huge time saver is that you're not going to distill the entire thing. You're not going to distill everything that's in here. All you're going to distill is until such point that you have collected 10 milliliters of organic layer, 10 milliliters of organic layer. So what does that mean? So you're probably going to distill a total of roughly 100 mils, roughly 100 mils. But you're going to have 2 layers. You're going to have an aqueous layer and an organic layer. The aqueous layer is going to be the lower layer. So let's say, let's say this is the aqueous layer, and it's going to be bigger. It might be something like 90 mils or so. And then the top layer is the organic layer. That's the one we're interested in. See, because all of our products are organic, and it's not always the case, but usually the organic stuff will be in the organic layer. So this is where we're going to find our product. And you want to have 10 milliliters of the top layer, 10 milliliters, and that's your organic layer. Soon as you have 10 mils of the organic layer, you're done. Do not waste time to continue to distill. It's a complete waste of time. As soon as you have 10 mils of top layer, finish it and move on, okay? Because otherwise this could take forever. Okay, so let's move on into our procedure. So what happens next? So you're going to pour everything you distilled into a SEP funnel, and then you're going to add a little bit of sodium chloride to help with the separation of the phases. And you're going to separate the organic layer from the aqueous layer. The aqueous layer is waste. So you're just going to discard that. We're not interested in the aqueous layer, but you're going to pour the upper organic layer into a dry 50 ml Erlenmeyer flask. And then you're going to add anhydrous magnesium sulfate to dry it. Okay, so if there's any microscopic amounts of water at this point left in the organic layer, that will take care of it. It is important that you add enough drying agent so that the drying agent that you added most recently remains unclumped, and you have sort of this, what we call a snow globe effect. If you're unsure what that's supposed to look like, ask a TA or a professor. After the drying agent has been added and it is clear, it's very important that it's clear, the solution, ask a TA, please, if you're unsure here. Then you can move on and into the next step, which is taking a gas chromatogram of your product. Okay, so what we're interested in here is to see how much of the cyclohexanol, which is the starting material, how much of it is left over. And on the basis of that, we're going to make an assessment of what the yield of this reaction was. Let's look at and I'm going to talk about the GC more in just a moment. But let's talk a little bit about waste and cleanup for today's lab. So the cyclohexanone, the product, you're just going to have a container that is going to be provided for you in the hood. You definitely want to make sure you don't put that down the drain, but you put that in that container. Whatever is left over in your 500 ml round bottom flask from the distillation, whatever you didn't end up distilling, that stuff can go down in the sink together with the aqueous layer as well. So those things that are aqueous, we can get rid of them in the sink. Make sure you have some water running while you're doing that, okay? All the glassware of today's lab should be cleaned with soap and water afterward, and you definitely want to use some acetone that's provided for you to rinse out anything else that has any residues. Afterward, make sure you clean up and make sure you clean up definitely any spills and don't have any remaining chemical spills for the next when the next group comes in. We want to leave behind a very clean and safe lab. All right, so now let me talk a few minutes about this gas chromatography, which is also something that you should know from Orgo 1. But again, you might only have done this in theory and not in practice. So we're going to analyze our product mixture by gas chromatography. So we're expecting that we have some product, which is the ketone cyclohexanone, and probably some unreacted starting material, the secondary alcohol cyclohexanol. This is what a GC machine looks like. We have a couple of different types. This is one of the older machines. And so it's important that you inject your sample where the right, so sometimes, or all of the machines have more than one port, and you want to inject it into the right port. Okay, the right port is marked. So you want to inject it into the right port. Be very careful. The port is super hot. Do not touch it or you will feel the burn. This is some of the newer GC machines that we have. For this one, the injection port is on the top of the machine. So this is the front face of the machine over here. And this is this is the front and this is the top. And the injection port is located on the top. Whereas for the old machine, the injection port is located in the front of the machine, okay? When in doubt, ask a TA, but it's pretty self-explanatory. Okay, so you're going to inject your sample. We're going to show you how, and there's going to be a detailed description of how to use the GC by the GC machine. Okay, so this is not included in your lab manual today, but we have instructions on how to use a GC that's going to be available for you in the lab. All right, and we're going to analyze everything with LabQuest. So you're going to connect the LabQuest to the GC, and the GC is going to show you your gas chromatogram. Definitely make sure you don't delete your data until you have confirmed with your TA or your professor that your results are good. And you can probably print out your GC. You can print it out, but it's also okay if the printer sometimes doesn't work. So if you cannot print it out, that's not the end of the world, okay? As long as you have your data, that's the most important part. So this is what the GC chromatogram will look like. And I want to tell you a little bit something about the analysis. So what you're looking at on the x-axis is time. And so the peaks come out in different times. And what we do with GC is we can separate, in this case, things on the basis of their boiling points. So compounds that have a lower boiling point will come out first, and compounds that have a higher boiling point will come out later. So in this case, we see something came out around, I don't know, 200 something seconds, and another thing came out around closer to 300 seconds. So this one was later in time. So on the basis of this, we can say that this peak over here to the right must have a more higher boiling point than the one over here to the left. So in today's reaction, we're looking at organic compounds. The first one is cyclohexanol, which is the starting reactant. The product, on the other hand, is a ketone called cyclohexanone. So the question is, which one of these two things will be which peak over here? So in other words, which one has the higher boiling point? And if you want to think about that for a moment, I encourage you to pause this video and think about it. Which one of these two could have a higher boiling point on the basis of some of the things that you know about organic chemistry? Okay, well, here's the solution. The cyclohexanone is an alcohol. The cyclohexanol, of course, is an alcohol, and therefore it is able to perform hydrogen bonding. Things that can perform hydrogen bonding tend to have really high boiling points compared to things with similar molecular weight that cannot do so. So long story short, the alcohol will have the higher boiling point. So the alcohol will be the peak that comes out later, and the ketone will be the peak that comes out sooner, okay? Now, based on the integration or the area below the curve, we can make an assessment on how much of each of these things was left at the end of the reaction. So this is the area under the peak, and the LabQuest will do the calculation for us. And then based on this area compared to this area, we can sort of make an assessment on the yield of this reaction, okay? All right, just a couple last things about safety. It is utmost important, as always, for you to wear your goggles and closed-toed shoes and appropriate clothing at all times during this lab. Please be careful when you're using the glacial acetic acid. While acetic acid is technically just vinegar and we put it in our salad, today we're going to be using super highly concentrated and caustic acetic acid. So this stuff is not to be joked with. Do not try to smell it. It's pretty, yeah, it's very acidic, okay? If you were to make any spills, please wipe that immediately. Be super careful with the Bunsen burner you're using today during the distillation. Again, I want to repeat, you're using the larger of the two Bunsen burners that you have. So be very careful with the open flame. As always, long hair definitely has to be tied back, and you want to be careful to not burn yourself, and definitely make sure you keep any of the hosing or any things that are flammable out of the way of the Bunsen burner. Once you're done, please clean up your hood and all the common spaces, including anything around the scales and everything, thoroughly, so that we leave behind a clean and a safe lab environment for the next group to come in. Thank you so much, and good luck with the lab.